Okay, so I was going to actually spend some more time preparing just now, but so it's going to be slightly disorganized, but hopefully not completely incoherent. Thank you so much for inviting me to give this talk, and I'm really sorry not to be there. It's visiting Bangalore is one of my favorite journeys, and it was a disaster for me personally, anyways, not to be able to come this time. So I'm going to talk about this notion of arithmetic field theory, and it's taking off somewhat right now. I think it's becoming sort of interesting due to other people, not necessarily me. But I guess I proposed this collection of ideas surrounding this a number of years ago. Didn't do much with it, but it seemed to be turning into something more interesting these days. So I thought it might be worth talking about it here. But because this is a conference on modular forms, I'm going to focus a little bit on the case of elliptic curves and modular curves. Right. So I was going to do a little bit of advertising, a YouTube commercial before my main talk, but since I'm late, maybe I'll skip that. This was a commercial for the program we have at the ICMS on Mathematics for Humanity, but I'll just mention that there is such a thing, and you should check our webpage, and I hope many people will be interested. So let me start talking a little bit about fields. So fields in the sense of physicists, not in the sense of number theorists, because I guess the people here are still gathered mostly to do number theories, so it might be not out of place to talk a little bit about the general background for the ideas I'm about to discuss. Now, fields, for a physicist, it's reasonable to say that, roughly speaking, anything is a field. Sorry, I think I need to reorganize my screen just a little bit. So any object is a field. I'm a field. So a particle is a field. Everything is a field, roughly speaking. Maybe even precisely speaking. But there's something to be learned from this perspective for a lot of mathematicians, I think, in number theorists in particular. So now, to make this slightly more precise, when a physicist talks about a field, usually they have in mind a fiber bundle over a manifold, which represents space-time. So M is some manifold of usually four-dimensional, representing Minkowski spaces, some more complicated Lorentz manifold. And you imagine having a scheme over it, or a fiber bundle, or more generally a stack. Right? And you talk about fields as being the sections of such a space. And so depending on what you're interested in, the space and the space of sections will differ. And setting this up, just saying the kind of space this is and how it fibers over M is usually called the kinematics of a theory. That is, what kind of mathematical objects make up the fields we're going to be interested in. So I'll give you examples in a second. But I should also mention first that the dynamics, the more interesting part of the theory, is usually formulated in terms of an action. So this is a function from the space of field to, say, the complex numbers or the real numbers, depending on the situation. And this captures the dynamics of the theory, because once you have such a section, such an action, you can look at its critical point. So those points are in the space of fields where the differential is zero. And then this is called the classical state space, which comprise from just a classical point of view, that is the coarse point of view, the possible states that the fields can actually be in real life. So this is thought of as dynamic because this is a space-time manifold. So if you write it as space cross time, any given solution can be thought of as something on space evolving through time. And so you can also think of this as the classical path sometimes inside the space of fields. But anyways, so you're interested in, of course, in physics, you're interested in how something changes over time. So you're interested in differential equations of this nature and try to solve them. But it's usual in modern physics to formulate all of this in terms of an action, to say there's a function on the space of fields with critical points give you the equations of motion. So a very canonical example is to when the space is the cotangent bundle of a manifold, then the space of fields will just be the differential one forms. And a very well-known action in that case associates to a differential one form, this integral of the norm squared of dA with respect to over the manifold. So now this, so you have to make some assumptions for this to converge. Of course, you could take compact support sections, for example, or you could assume that the manifold itself is compact. There are a number of ways to make this precise, or you could put some boundary conditions and only integrate over a region. So, but anyways, roughly speaking, it's this kind of integral that's the typical action that physicists consider. I call it max because it's sometimes called the Maxwell action, partly because the Euler-Lagrange equation, the critical points of this action correspond to this equation, which together with the obvious equation saying that dDA equals 0, comprise this what's called the Maxwell's equations for the electromagnetic field. That is, if this is a four-dimensional manifold, dA will be a two form, so it has 6 components. And those are supposed to be the 3 components are the electric field, 3 components are the magnetic field, and this equation give you the usual vacuum Maxwell equations without any charge or current. So this is kind of a typical example to keep in mind if you are not used to thinking about fields and physics. This can of course generalize to the situation where you have a non-trivial line bundle over your space and consider the space of connections on the line bundle. So the previous case is when you have a trivial bundle. Also, another very common situation is when you consider one of these tensor bundles. So the bunch of tensor products of the tangent bundle tensor with a bunch of tensor products with the cotangent bundle. So that might be your fiber bundle, or you can take subspaces, quotient spaces, and so on of this tensor bundle. So very important instance is where you take inside the second tensor power of the cotangent bundle the space of metrics, the non-degenerate quadratic forms on the tangent bundle, non-degenerate pointwise. In that case, there's a very famous action which starts with a metric, takes the scalar curvature, integrates it over the manifold, and this is called the Einstein-Hilbert action, whose critical points exactly give you the vacuum Einstein equations. This is again just to give you a basic feeling for fields and actions. But another important, the last example, I guess I'll give you is when the fiber bundle is just a product, M cross sigma for some other manifold, sigma. And in that case, well, this kind of thing is, physicists seem to call it a sigma model. I don't know why, maybe because somebody also calls the manifold sigma. But anyways, the fields in this case, the sections of this bundle can be just identified with maps from the space-time manifold to sigma. And so that's also a very important class of fields. So, for example, when you're doing string theory, this kind of field is kinematics. But now, if sigma also has a metric, then you can do something like taking d of phi, taking the norm squared of that in an appropriate sense. So this will be a section, if you'd like, of the pullback of the tangent bundle of sigma tensored with the cotangent bundle of M, right? So there's that has a metric, and there's the norm squared there. Then you integrate it over M. So that's a action, a function of maps. And these critical points are sometimes called harmonic maps. It can also happen that the sigma is equipped with a bunch of other fields. I said a metric, that's a kind of a field, but it might be equipped with a section of a spin bundle or various auxiliary objects like that, which help you to define such an action, or different kind of action as well. So flexibly thinking about what kind of ways to modify this or refine this or enhance this to get interesting actions is the kind of thing physicists do all the time. And we can also learn from the kind of things they do. Okay, so that's a brief review of what physicists mean by fields. But sorry, I guess the last thing I want to talk about is I spoke about actions. Now, actions typically take this form. They're integrals over the whole manifold of something that looks like a quadratic function of the fields, typically, plus some higher order terms. This is what most of the actions that physicists are interested in look like. But there are other functions in field theory, other functions of fields that that are not as global as this. This really will depend on, of course, the way the field depends on. So, I mean, so typically you have a density that you integrate, and the density will be made of what people call local functions of the field. There's some pointwise function, the value of the field, derivative of the field at a point, and things like that. But then you integrate it. So that's what an action looks like. But there are other important functions in field theory that are supported only on submanifolds. And these seem to be becoming very flexibly thinking about such things using the machinery of, in fact, higher category theory seems to be becoming very important in these days. It's one of the hottest topics, I think, in mathematical aspects of quantum field theory. So a good example, which in fact is the only example I understand, is when the space of fields is the space of connections on some principal G bundle P. Right? And then the manifold might be a knot, or we can be slightly more general, and the submanifold, that is, slightly more general, and consider a map from the circle to the manifold. And so that's what I'm denoting by K. If you further fix a representation, a finite dimensional representation of the group G, whose under which you have the principal bundle P. So G might be typically a compact Lie group. In usual physics, SU2 is an important case. And you just fix a finite dimensional representation like the standard representation of SU2. Then you get a function of fields again, in this case. And this is very natural, right? Because what you can do is you can take a connection, restrict it to the circle, compute its holonomy. Then you get an element of G, which will then act on this representation V, and you take the trace. So this is sometimes called the Wilson loop function in gauge theory by physicists. And things of this sort are ubiquitous in number theory as well, which is what led me to think about the ideas I'm presenting today. Okay. In quantum field theory, you are not just interested in actions and these equations of motions or critical points of actions. You're interested in integrals like this. So this is the action up here, L phi. Right? So that's some number, and you exponentiate it with some suitable constant. Exactly what constant, as we put here, is not important for the purposes of a course talk like this. When you take some exponential of the action, and you integrate it over the space of fields. When you just integrate like that, this is sometimes called the partition function. Of course, it's a number, but it might be a function of other auxiliary things that you have in here, but it's called the partition function. So for example, there might be a temperature here that is a function of and so on. But anyways, as it is, it's just a number, the way I've expressed it here. It's an integral over a space of all fields. More generally, you have things that are sometimes take the shape of correlation functions. You might take other functions of fields here, right? Like these local functions that are supported on submanifolds, or it might be very local, like it might just be the value of the field at a point. Each one of these things has some specific collection of points. And then you integrate that with respect to, now from the point of view of these correlation functions, you view this exponential times d phi as comprising a measure that you're integrating with respect to. So it's not an exaggeration to say that in serious physics, of quantum field theory and when people want to make predictions about scattering experiments and so on. Computing functions like this is all you have to do in principle in order to get all the quantities that are of interest in these particle accelerator experiments. Now, but the problem is that these are typically ill-defined from a mathematical point of view. Any normal computation of such a thing gives you infinity. So physicists do a lot of things to extract approximations to this integral that yield finite quantities. Approximations themselves are also infinite typically. And so there's a whole very technical machinery for extracting numbers out of this. But from a mathematical point of view, it is ill-defined, and some people regard it as a very important problem to define these things mathematically. The opinions differ. There were some people for several decades who really did try very, very hard to do hard analysis to define these things. And then people kind of got bored with it and did other things. From a mathematical point of view, I like to view this problem as being Zeno's paradox, because it's like the classical Zeno's paradox you see in stories, because we know that these are supposed to give you some numbers, and these numbers can be observed in actual experiments. So we know that the quantity should be finite, right? Like the amount of time that the arrow takes to reach the target. So that's finite. On the other hand, any method that we apply to actually compute it gives us infinite. So it's like the misconception that existed in the old days. So we don't really know how to sum these things properly to give the results observed in nature at the moment. But in spite of that, they are tremendously useful guides for plausible computations and formulations of mathematical conjectures as well. So thinking about formal properties that these kind of integrals have to give rise to conjectures. This will give rise to definitions from a mathematical point of view of things like conformal field theory or topological quantum field theories. Well, so from that point of view, once you've defined something like this that has those formal properties, it might be an invariant of the manifold, for example, or might be invariant of these quantities that define these functions. For example, knot and link invariants all arise by giving the correct mathematical interpretation of quantities that have the properties of these path integrals. Okay, so that's a lightning review of the physics that's relevant to our discussion. And now I will review another topic, which used to be kind of a curiosity, and I think it's becoming more interesting and important in the last 10 years or so, sometimes called the arithmetic topology. There are many different angles to this story as well, and I'll just focus on one. So here, the basic idea is that if you take the ring of integers in an algebraic number field, then its spectrum has many of the properties of a compact closed ring manifold from the point of view of, say, Grothendieck topologies like the Tal topology or the FPPF topology. I hope I'll have time later to review a little bit of how this goes. But for now, I'll remind you that the most naive reason for thinking of this as being like a three manifold is because if you take a residue field, that's a finite field, and then spec of the residue field gets included inside spec of OF. And we know that the spec of a finite field having fundamental group Z hat is supposed to be like a circle. So one views this as being analogous to the inclusion of a knot. Right. Once you do that analogy, then a lot of other things follow. So for example, if you complete OF along the knot and take its spec, so that algebraic geometers are used to if you complete along a subscheme, for example, that is an formal algebraic version of a tubular neighborhood. So this should be like the tubular neighborhood of a knot, or in other words, a solid torus surrounding the knot. And then spec of the completion of the field that is also obtained from that previous tubular neighborhood by just deleting the closed point at the center, which is supposed to be like the knot being deleted from the center of the solid torus. So then there should be like a usual torus or two-manifold, because that's homotopic to a two-dimensional torus. So along this line of analogies, finally, if you take a finite set of primes and just remove it from the spec of OF, then that's like removing a bunch of knots out of a three-manifold. So that should be homotopic to a three-manifold with boundary. So in other words, if you think about this as being homotopic to removing the whole solid toroid, that is the tubular neighborhood of the knot as well, then you get a three-manifold with boundary, and each boundary will be correspond to a torus, right? Spec of FV being a torus. So you think about the disjoint union of the spec FV is for A running over B, mapping to XB as being like the inclusion of the boundary inside the three-manifold with boundary. So fine. So these analogies go back to the 1960s, and then people did different things with it, and like very interesting things. Like Morishita did a lot of interesting things in since the 1990s, I think, and then Kapranov and Reznikov and so forth. A lot of people did a number of things with it. Now, for me, I think the really interesting story begins from a dual interpretation. That's just personally. What I found interesting is this dual interpretation. What do I mean by the dual interpretation? Well, if instead of the spaces themselves, like spec OF or a three-manifold, I can instead look at spaces of connections, flat connections or representations of the fundamental group. So you can fix a p-adic Lie group, say, as a target, corresponding to a compact Lie group target that people might be interested in topology, and then consider representations with values in R. Now, it's not so easy to make this into an actual scheme or a stack, but for the moment, it obviously has a kind of geometric nature, so I won't worry about the foundations of the algebraic geometry of such a thing, or analytic geometry, and just speak about it as a space without being too precise. But anyways, once you think about this kind of thing, of course, this is much more analogous to space of flat connections on a three-manifold. Then that's a better analogy than analogy between the spaces themselves. Because this pi1, of course, is probably better analogous to pi1 of a three-manifold. So, and the key point is that here as well, you can take a pair, a point of XP that's supposed to be analogous to a knot, right? And a finite dimensional representation of this group R. Okay. Then we get a function. This is a well-known function to number theorists on spaces of representations, right? Simply take the Frobenius at X, evaluate the representation. I take rho of that. It's a conjugacy class, but it won't matter. Right? And let it act on the representation B and take the trace. So this is the Frobenius trace, simply, right, on this representation V of R. But of course, this is entirely analogous to a Wilson loop, as discussed earlier, considered by physicists in gauge theory. So this is the dual interpretation that is thinking about primes as functions on these moduli spaces is very analogous now to thinking about knots as functions on moduli spaces. That's much better than the original knowledge. And once you've set this up, you can start asking other questions too. The obvious question for me anyways being, what are things like actions? Are there actions in this situation on these moduli spaces? Are there paths? Can you do integrals, path integrals over moduli spaces like this instead of spaces of connections and so on? And then, of course, you might also wonder if there are other moduli spaces that one can, because of an arithmetic nature, one can consider from this perspective. Maybe I'll just also briefly mention that how this, although we're not going to really stress that in this talk at all, how one sets up an arithmetic topological quantum field theory. So this is how it would go. This entirely mimics what happens for manifolds. And of course, I haven't defined it in that setting as well. So I'm sort of defining it all at once by just discussing it in the arithmetic context. But if you had an arithmetic topological quantum field theory, what it would do is it would assign to something like this arithmetic three manifold spec of a ring of integers, right? A single number. So this would be is supposed to arise as one of those path integrals. Will have some fields on X, and you'll have some action, and you'll have a path integral over all fields of exponentiated action. So that should give you a number. That's the idea. And then, but the other aspect is that to the local fields, this theory should assign a vector space. So where is this supposed to come from? Well, whatever these fields are, I didn't give you any examples yet, but whatever the fields are, they come with boundary conditions. What kind of values can they take when you restrict to the boundary? For example, you might consider just restricting a Galois representation to a local Galois group. Then, so there's a space of boundary values of fields. Right? But then, in quantum mechanics, when you have classical fields, the quantum version of it is roughly the space of functions on the space of classical fields. You have to put various conditions on it. The easiest thing you can do, well, mathematically, the easiest case to think about is you put a complex structure on the space of classical fields and you consider holomorphic functions. That's one version of the quantum Hilbert space that you obtain by quantizing these classical fields. So you're supposed to get the space of functions, imagine the space of functions and the boundary conditions of the field as being associated to the boundary of a three manifold via this theory. But then you can associate the manifold with boundary itself also gives you a vector in this theory. So I will actually, so I've sort of explained this in a single line why you should expect to get such a vector. I won't dwell on this very much, but it's very interesting, I think, this construction, and I won't be able to discuss it today, but there are examples of this which can themselves be viewed as invariants of primes in some way. So when you do the computations here, so for example, when B consists of two primes, you can get vectors of this sort to reflect the Legendre symbols, classical number theoretic invariants. So there's a way in which you can incorporate inside this formalism classical number theory, but also formulate new invariants. Anyways, this is just the setting of a little bit of the language that I'm not really going to use today. But this conference is supposed to be about modular curves, so I will say a few things about modular curves. Anyways, so the examples I'm going to discuss here are a little bit artificial, but I didn't want to say something about modular curves, so I squeezed them in. Well, but you see, the point was already contained inside the general framework that I set up, that you can consider various fiber bundles and sections of that as being field. So for us as well as number theories, we can consider anything as targets of fields, right? So, for example, if you had an S scheme Z, right? Then for any other S scheme, we can consider sections of Z over T, right? So we can consider that as a space of fields and ask, what are the natural functions on the space of sections? So if we do this to modular curves, then we see that number theorists have already done things like this quite a lot, right? So if in the case where you have the stack of compactified moduli stack of elliptic curves, right, then the sections will be generalized elliptic curves over, say, the spectrum of an algebraic number field. And then we already study lots of functions of such things of a natural side, right? So, for example, a natural action might be the faulting side of an elliptic curve. We know how to define it by taking, well, other than I'll explain this factor 12 in a second. but I hope I'm getting this 12 right. I may have miscomputed something, but anyways, if you take the invariant differentials on E, right, then that has a natural metric as well as, of course, it has an integral model over all places. So you can take its degree as an Arakelov line bundle. And that is very much like a global integral over T. Right? So you're considering the contribution from all places and taking a sum. That's how you compute this degree. Okay, so it is very much like a global action that you associate to any elliptic curve, which, remember, is a section of this compactified moduli stack of elliptic curves. In other words, this is a function, natural function of the space of sections. This 12 here, I'll tell you the reason for it in a second, a mathematical reason, more precise reason. But if you'll recall, if you take 12 here, this is the quantity that becomes roughly comparable to the discriminant. And if you remove the 12, that's like the 12th root of the discriminant. Well, so an easy lemma is that now if you exponentiate this and take the integral over all the sections, in other words, take the sum over all elliptic curves, then this actually converges. So I hope I did this calculation correctly. Well, anyway, so the proof is very easy. It follows from a theorem of Ruthie. I don't know if I'm reading the name correctly. And there are the earlier versions of the theorem, but I'm just citing the latest one that was formulated in terms of halting side. That if you look at those elliptic curves such that 12 times the halting side is less than b, that behaves roughly like e to the b 5b over 6. So if you consider that, you'll see that you get convergence. Compute this up. So this partition function, in other words, for the faulting side, viewed as an action in some sense, right, is a finite number. So I think I don't think sums of this sort have been considered before, but they're interesting to consider. So I think that's what I'm suggesting, that I'm starting from a physics view that you may like or not, but they do seem to generate interesting things to focus on and try to compute. What about these local functions supported on submanifolds? Well, we all know some very, very well, right? So for example, you can take a prime and consider the standard AEL associated to an elliptic curve, right? So p plus 1 minus the number of points. So this is a very well-known local function that's clearly supported only at a single prime, in other words, one of these arithmetic knots. But once you have something like this, the quantum field theory perspective makes it irresistible to try to set up integrals like this and compute them. I'm not going to be able to do this. I'm just posing this as interesting quantities to consider. So of course, this is absolutely convergent because these AELs are all bounded. The previous thing was convergent, but the exponential term made it convergent. But it's interesting, it seems, to consider products of this. So correlation between the AELs, I think, are very much have been considered by number theorists in various contexts. But what I'm proposing is that weighting of this, or the exponential weighting, is an interesting thing to do that's suggested by physics. Here are some other functions. So this is also probably well known. I haven't really seen them in the literature. So here's a function on x1 of p. So here you'll have an elliptic curve together with a p torsion point, right? So in that case, one interesting function is you can take a prime congruent to 1 mod p and fix an isomorphism between the pth root of L. Remember, with this condition, the pth roots of L will be rational over FL. Fix an isomorphic to complex pth root for each one of these L's. Now here's a function, local function on x1 of p. So given an elliptic curve E and a P torsion point, and I can compute this quantity. Let me explain. So if I take the point reduce mod L like this, right? Then that's a rational point, but I can take its box time under the map from EP to EP squared to EP. Now, for that to be well defined, I need to choose L also fairly carefully, avoiding, for example, the easiest way to do this is to avoid the primes of bad reduction. And you can do this for primes of bad reduction as well with more assumptions and care. But anyways, if you take L here initially to be just a prime of bad reduction, there's a Box-Stein operator that will take this rational point to an H1 class. Okay? So then I can pair it with the original rational point. So you get a quadratic function of the rational point. Then the pairing, I'm just writing out a well-known duality pairing between H1 and H0 over a finite field. That is, I can take this H1 class, choose a co-cycle representative that will be a map from the Galois group to EP, and just evaluate it under Frobenius element that will give an element in EP that I'm taking the wave pairing between that and X. So, of course, the co-cycle representative needs to be chosen, but when you take the wave pairing with a rational point, that choice goes away. So you get a number, a p root of unity this way. Associated to, what do we have? Associated to a prime L. Right? So that I'm calling that TL. So this is a kind of local function, an x1 of p. Hey, it's kind of interesting to try to cook up functions of this. Probably some of them were well known, maybe not. But I think you do start asking more questions about local functions, global functions, and things like that, if you start from the perspective of quantum field theory. Well, so once you've set it up, again, it's interesting to try to compute the integrals of this sort. So now I'm just posing these as problems. I don't know how to compute any of them. Well, maybe last example of the modular curve sort is to consider the moduli stack of curves of genus 1, that is the ones that don't necessarily have a rational point. Of course, this admits a map from the modular curve, right? Because by forgetting the point, also admits a map to modular curves by taking the Jacobian. So in this case, so I thought, I initially thought that I could think of some natural local functions on this thing. But I somewhat failed. I thought I had something I couldn't remember how to do it. So here's a slightly artificial example, but maybe it's still interesting. Consider the sections of M1 cross M12 fiber product over X1. This is genus 1 curves equal to 2 points, right? So 1 point can be used as the origin, and there's an extra point here. And then these both map to, I guess I need to be slightly careful. Yeah, I guess I need to hear ordered points or something in order to get the map from M12 to X1. I need to order them so that I can forget one of the points. Yeah, sorry about that. Anyways, so here you should consider sections of this. So then, what does this become? The sections of this can be considered as being what? An elliptic curve or torsor for the elliptic curve. That's the genus 1 curve, right? And then a point on the elliptic curve. Yeah. So those are the sections. Well, then it's very easy because you can take a prime of good reduction, for example, and pair again the torsor and the point. Oh, sorry, you don't, sorry about that. You don't do this for reduction mode, but you do this in the local field. Right? Then you get the local Tate pairing between points and H1, and get an element of Q mod Z. So this is another example of an interesting, I guess the way I set it up, it really depends on this torus boundary, not just on the elliptic, and not just on the knot. So that's a bit interesting. But this is a function on this slightly contrived moduli stack. And then you can try to compute this kind of integral. You get a bunch of roots of unity again by exponentiating. You have this measure coming from the faulting section. Try to integrate it over F. So those are the basic examples that to me are interesting suggestions that come from physics and things to try to compute. So let me finish up by giving you a few more examples of arithmetic actions in a slightly different context where one can actually compute things. So in a way, these are easier. Well, yeah, they are easier than the previous examples, but I put it at the end because they don't necessarily have to do with modular curves. So because of this slightly complicated the complexity that arises with duality theory, if you have real places, let me assume that now here with the number field is totally complex. So in that case, I'll go back to the original moduli space I mentioned at the beginning, moduli space of representations of pi 1. And we'd like to, what would we like to do? We would like to define functions that behave like actions, well, and possibly local functions, as well as path integrals of this sort. Now, and I'll also consider some related moduli spaces as well if I have time. So here's one easy way to do it. So it uses sort of the general duality theory of these fields. So if you take the nth roots of unity, oh, sorry, I should have said, let me assume that in fact F contains the nth roots of unity. That will make it totally complex for n bigger than 2 anyways. Right, the basic fact is that H3, a tau cohomology H3 or flat FPPF is the same for X with coefficients in mu n will become isomorphic to Z mod n canonically. And this just comes from the usual class field theory computation where you consider this. Yeah, I guess for this discussion, I should make it the FPPF for this to be an exact sequence. Anyways, if you do this, you'll find that H3 with coefficients in mu n is just isomorphic to the n torsion. There's some further vanishing theorem that kicks in, and then it becomes the n torsion of the H3 of GM. But H3 of GM is Q mod Z. This is essentially the same as the reciprocity sequence for H2. But now using that, well, I guess I sort of explain it here. And this comes from this local class field theory and reciprocity sequence. So this Q mod Z at the end is that previous H3. Yeah. Now using this, it's easy to define functions of finite Galois representations, and also with suitable limits, you can even do this for p-adic representations. But there you run up with a lot of problems of limits that I can't resolve very cleanly at the moment. Yeah, so therefore right now, let me mention the finite case. If you consider H3 of pi 1 rather than H3 of X, then that will map to H3 of X, which is Z mod n. Now, but in general, of course, H3 of X is more refined than H3 of pi 1. So for example, pi 1 might be trivial, but in any case, you have a map. So, yeah, I think this was a kind of extraneous remark because this slide was recycled from some other talk there. The orders were fixed up, so I think I have some extraneous sentences here. But anyways, now on the space of representations from pi 1 to R, for p-adic Lie group R, you can try to define Chern-Simons functions like this. A function, which is actually, I used this word now, this is what's an analog of a physicist called the Chern-Simons function. What you do is you first fix a cohomology class of R with coefficients in Z mod n. So a priori, this has nothing to do with arithmetic. R is just a group, periodically group. You take a group cohomology class. And having fixed such a class, you get a function of representations in an obvious way. So how do you do it? Given a representation that's a map from pi 1 to R, right? So you can take this class C, pull it back to get a H3 class of pi 1, which then we mapped to H3 of X, then maps to Z mod n. So that's the map. So that's an easy way of getting a finite valued map of representations. So that's one example. So an easy case is if, well, when R is itself the finite group Z mod n, in that case, this moduli space is simply just H1 étale cohomology with coefficients in Z mod n, or dual of the class group, some dual, Z mod n dual. Now, you can take, in this case, the cohomology class as being a cup product of this sort. You can take A to be simply the identity from Z mod n and Z mod n, viewed as an H1 class. And then delta of that, again, coming from the Box-Stein sequence, will give you an H2 class. So if you take the cup product, you get an H3 class. Now, if you do that, then you see that the Chern-Simons invariant of a representation is simply this invariant applied to this H3 class of pi 1. So this is very similar to what people call abelian Chern-Simons function in topology. It's the formal expression is actually identical. So it's like integrating A dA, A wedge dA for a connection. Now here's another example. So this is slightly abstractly, you can start with a finite n-torsion group scheme, and it's a dual group scheme. And under certain conditions, suppose, for example, this finite group scheme admits the Box-Stein map. So I guess I should have written it here, but in other words, you might, you might have an extension like this, V by V. In that case, you would get a Box-Stein. It would depend on the extension, of course, but you get a Box-Stein map out of the situation. In that case, you get a function, this two-variable function, just by taking A, B to the invariant of dA cup product B, right? Because dA will be an H2 class, which then gives you, when you product with V, will give you an H3 class, again with coefficient in mu n. Then you'll get this kind of BF function. This is a terminology from physics that doesn't make any sense in this context, but I'm continuing to use it. You get this two-variable function. So that's another example of an arithmetic functional of some sort. So there's various fluff to motivate this discussion. But what I wanted to, I'll skip that, and what I wanted to do was show you some computations anyways that I did with some collaborators. This is joint work with these people, Hee-Jung Chung, Do-Young Kim, George Papas, Jiwon Park, and Hwa-Jung Yu. So for this is a very simple case. Suppose you take n to be a prime and you assume that the Box-Stein map is an isomorphism. This last assumption is not strictly necessary, but it makes the formula easier. In that case, the analog of the path integral, right, is you integrate over rho this kind of abelian Galois representations with coefficients and values in Z mod n. This exponential 2 pi I now, this Chern-Simons function, this will be a pth root of unity, right? And now this we can evaluate. If you do it, you get an expression like this. So it's kind of intriguing, I think, because this is a rather simple exponential sum, right, of roots of unity, and you can get a square root of the p class number of it out of this sum. And there's a sign here given by the Legendre symbol, and there's another sign here. But anyways, The Shaunak, but maybe I'll comment on that briefly. D is a map from a map space H1 to H2. H2 in this context is the dual of H1. So this map is a map from H1 to its dual, and its determinant, such a map is it has a well-defined determinant of 2 squares. So in this side, this Legendre symbol, it's well-defined. So you get an expression like this. So it's somewhat interesting because when you do these kind of integrals in usual physics, you do also typically end up with determinants and other invariants. In this context, it's interesting that you get the square root of the class number, which doesn't come up easily in usual number theory. The BF theory case is also somewhat interesting. Which is, suppose you take the group scheme to be mu n, and then the dual will be z mod n. So there was this 2 variable function that I defined earlier using the Box-Time operation. What happens when you do the sum over all AB of exponential 2 pi I of this z mod n valued element? So again, this is a sum of root of unity. So here, I'll to simplify, I'm stating this only for n sufficiently large, although you can modify it again for smaller n too. When you do this, you get a quantity like this. It's very simple. And the proof, by the way, is very simple application of arithmetic duality theorem. So I'm not claiming I'm doing anything deep here, but it's still suggestive, as you get something like a class number term and something like a unit term, something that looks roughly like the regulator, right? So that is, it's suggestive to compare it with this kind of class number formula. Of course, it's much easier than the class number formula, but I claim that it is still rather suggestive. So the previous integral or sum for the Chern-Simons case gave you square root of the class number. Here you get the class number itself. Now, there's also an elliptic curve version of it. So here I'm running out of time, so maybe I won't set this up very carefully, but you can also do this with the n torsion of an elliptic curve, which under suitable assumption will be self-dual. And you can do the integral again over all elements of this space of fields H1 plus H1. In that case, you get Shah and again a regulated term. So it's very mildly amusing here that you get square of the model or mod n, which is what you should get. That's what the regulator of an elliptic curve is, right? And it seems to come out correctly that way. Yeah. And it's the square of a volume that is the regulator, and you get a square of the model V type term for this sum as well. So this is very suggestive of this formula that occurs in BST. So yeah, I don't think I have much more to say about this. I did want to say more things about this eventually, but because of my silly miscalculation of time, I've mixed things up quite a bit. So I'll probably skip the rest of the lecture, but I think it's these are very easy formula by comparison with the things that you do with L functions. But that's the point. Although it's a very ambitious and probably widely speculative idea, I'm hoping that these easy formulas suggested by the formalism of quantum field theory might give us some insight eventually on these very deep and difficult formulas. Okay, yeah, I'll stop there.
You can take 10 minutes if you want, and maybe show us some of the other ideas as well, if you want.
Let's see, let me say what well, actually, yeah, well, okay, let me, yeah, oh, thank you very much. Let me just say one thing, by the way. So here, if you just take the BF applied to a comma a, right? So here, remember, it's a 2-variable function, but you could take a equals b. So then this becomes very much like a Chern-Simons function for elliptic curves. And this turns out to be mod p version of the p-adic height. Well, what do I mean by that? Well, what I mean is, you can do this, if you do this p-adically, right? rather than mod p. And you use for the Bochstein operator something coming from IISer theory, an exact sequence coming from IISer theory. Then this turns out to be exactly the cyclotomic periodicite. That is, when you apply it to an A coming from a point. So there's a kind of natural congruence between these Chern-Simons type constructions and the theory of periodicites. And this is why I then went back eventually and thought that maybe we should think about Archimedean height and try to consider path integrals for those as well. But the last thing that I think is interesting to compute, so remember the difficult computation, I haven't even attempted to do that. I'm just suggesting it to other people. But in this context, there is one computation which I think is a little bit interesting and is accessible. So here's what it is. So again, let's take L to be congruent to 1 mod P, and as before, as in this other discussion. And now in this case, we'll fix a L point. I think maybe I should take up order PL point, FL point of order P. So this is like a local operator now, really, because what do you do? So there's 2 bits of data, this thing that's like a knot, L, right? But then an additional bit of data. This is like the representation in the Wilson loop in some sense, right? So in that case, you get a function. How do you do it? It's the same kind of thing as before. You take some A in here, reduce mod L, sorry, right? And then take the pairing with Y, right? Considered as an H1 class, which, well, for example, you can do it by choosing a co-cycle representative, evaluating under Frobenius, and pairing with Y. So this way, you get something that really looks very much like a Wilson loop operator in a slightly different context for this space of principal bundles for the Peter for this finite group scheme. It depends on the prime data and an auxiliary data that's really local at L, right? But it's sort of behaving like this choice of representation. So you get this local thing. So what I wanted to say, since you gave me a little bit more time, is that this quantity I think should be possible to compute. And the previous things with the Archimedean height, it's hard to know even what you mean to compute it exactly. And I don't know whether you would get interesting formulas. Here, I'm reasonably confident you would get interesting formulas, and it is quite accessible. Yeah. So I should have said, in fact, that you can also do in this path integral as well. For example, this one, you can do it with Wilson loop type operators inserted in as well. And then you get kind of arithmetic analog of linking numbers between primes. So I did want to propose this computation as something that should be interesting. But already I've strayed away from modular curves, maybe a little bit too much. Yeah, so I guess I will stop there. Yeah. Thank you very much. And sorry again for being late.
Thank you very much for that very interesting talk with many novel ideas. Any questions?
Yes, hello, and thank you very much. About the first of these formulas you gave with the square root of the class number.
Yeah, yeah.
It looks very much like the formula for the Gauss sums, right? Is there an explanation?
Yeah, yeah, very much like so. Like that. Yeah, you mean where you get square root of discriminants, right?
Yes, and even the power of I, which is usually very difficult to compute, appears here as well. So, oh, very difficult. I mean, not easy even for Gauss.
Yeah, I agree. Yeah. I think, yeah. Okay, now I don't remember. I maybe one even uses some version of those ideas in improving this formula.
Just a small second one. You did the other computation for elliptic curves in the next slide or the one after.
Right, this one. Sorry.
Yeah, this one.
This one. Mm-hmm.
I have a guess for the case of an abelian variety.
Oh, yeah, it's the same. Yeah, I stated it for elliptic curve because somehow this is a modular forms conference, but yeah, it's the same. Yeah.
Yeah, okay, thanks.
Except you just have to use the dual abelian variety on one side. Yeah, thank you for the question.
Hi. So in between, you showed a sum involving the APs actually.
That was the way at the beginning, right? Yeah, you can do that, by the way, here as well. But that was in the Archimedean context, right? Way at the beginning. Right here, yeah.
Yeah. So I mean, you have computed it. I mean, what is it, and what does it entail actually?
Here I have no idea, and I don't really know if it's even that interesting. But I think numerically, this might be a more natural correlation to look at than the usual things. Yeah, I mean, people do consider correlation between AL and AL dash as you run over elliptic curves, right? And but I'm just in a sense suggesting that physics would suggest rather that you weighted with some other global thing like this exponential. No, I don't know how to compute it. That's the short answer.
I just had a remark about I think it was maybe the previous slide where you do the sum just over the e to the, that sum there. I think basically, actually, I think something very similar came up in the last talk.
Oh, is that right? Gosh, sorry, I missed it.
No. So he was talking about the height zeta function on a modular curve. And I think that's the same thing if you add an S in between the 12 and the H. And he was using that to study generalizations of the Batrov-Manning conjecture. So, well, I don't know if it's exactly the same because I don't know the area very well, but it seems like
no. I mean, I guess you mean so there. Given a modular curve, you can look at height zeta or any variety. There are height zeta functions associated to the height of points, algebraic points, right? So that's what you're talking about, right?
Yes, yeah, and it's 1 over capital H of x to the s. So where capital H.
Oh, you're right. Actually, no, you're completely right. This exponential is actually the capital H, of course, essentially, modulo some normalization. Yeah, so you're right. I get okay. You're completely right. I had missed that point. This is I guess a special value of the height zeta function, or part of that. It's a small bit of the height zeta function because for the height zeta function, I guess you would do things like run over all algebraic points or run over all rational points on a variety with many rational points and so on, right?
I think, yeah, and you take the limiting behavior and there's a special value, and yeah, he was actually also doing it for this exactly. He was doing it for moduli stacks of elliptic curves. So.
Yeah, no, you're right. Somehow I hadn't thought about it. Yeah, thank you for pointing that out. Yeah, this should be related to the height zeta function. It's interesting. So the height zeta function, from this point of view, there's a special value of the height zeta function should be like the partition function of physics. But that, I guess, is the assertion in this context, thanks to your interpretation.
Any other questions?
So I have a question. Hi, Minhyong. This is Mahesh.
Hi.
So,
yeah, I'm sorry to talk about these superficial things. I mean, in front of you, I was a bit ashamed, but anyway.
No, sorry. So this formula with the Tate-Shafarevich group, I have a naive question about it. How do you use, I mean, why do you need the assumption on finiteness of Shah? Like, exactly how does that get into your group?
Let's see. I don't think I need it. Yeah, thank you for printing that. I think I modified these slides from a version of this where we were taking some limits to get Shah itself to appear, I think, somewhere.
Okay.
Yeah, I'm reasonably sure. I wouldn't swear to it right now, but for here, I don't think we need it. Yeah, thank you.
And this kind of interpretation, does it see ranks at all or not? I mean, like you compare this with L functions and there you see the rank as order of vanishing.
Well, the rank would appear, I guess, in here, right? Because
Please.
this would be n to some power, right?
Yeah. Okay.
Yeah.
So okay. So in this limiting thing that you just mentioned, maybe you get some kind of rank.
Right, but I get that's probably that. Yeah, I'd have to think about that a little bit. But I think the naive answer is that it is encoded in here, right? Because
Okay,
it is
yeah.
n to r, right?
Right, up to whatever the torsion.
That's right. Yeah, that's right. But for example, if you took n to be prime to the torsion.
Right. Okay. Thanks.
Yeah. No, thank you for the comment.
If there are no further questions, let's thank the speaker again for the wonderful talk.
No, thank you for the invitation. I'm sorry for so many things not being there, showing up late, etc., etc. But thank you again for listening.
Well, we hope you show up to India sometime soon physically as you were planning to, and we hope to.
Oh yeah,
look
I'm
forward
planning
see
to
you
come
there.
next year, of course. Thank you.
Okay. Okay. Thank you very much. Thank you.
Okay, bye.
Bye bye.